Hello. So here we're going to see where we were in terms of overall discussions of ignition. If you recall, last lecture we talked about liquid ignition, and before that we talked about spontaneous ignition. We want to change gears just a little bit by talking about solid ignition. And so the majority of fuel elements, fuel packages in a fire will be solid or condensed phase materials. For such problems, it's very important for us to understand what the overall dynamics are. And before actually going into detail about the theory, I'd like to show the relevance of solid ignition problems. So we're going to, again, switch to a video series that's available on YouTube. And this is the reaction to fire test for fluorine. So just to guide you through this, what you're seeing is a flame that's an ignition source that's a pilot, and what this test does is it measures the spread rate over, in this case, fluorine specimen, with the idea that there is some sort of external heating that's provided by this inclined radiant panel. So this is an inclined radiant panel, provides preheating on this fluor assembly or fluor material. And then we look at the flame spread rate over this material with this amount of external preheating. So this is a typical type of test that wall assemblies and floor assemblies are subjected to. So let's just take a look at this. So we see the heating process, and we see this flame spread process that's occurring on the material. So one of the things we're going to look at in the next lecture is the dependence on the flame spread rate on the ignition time. So the issue becomes that ignition is required for flame spread to occur, and flame spread itself is just a continuous ignition process. So as we talk about solid ignition, let's take a look at what's required for this piloted ignition of solids. So the idea is that, let's just draw a picture here. So imagine that you had this radiant panel that's incident on some solid material. There is, for example, a radiative heat flux on the solid material. So we have a source of energy, we have an exposed material. The radiant source is going to set up a temperature profile in this solid. So the solid might have been initially at some temperature T0, and as this heat flux interacts with the solid, the interface temperature is going to increase, and there's a penetration of this thermal wave into the solid material. As we get this thermal propagation, thermal wave within the solid matrix, the solid molecules or polymer strands begin to decompose. And so we, for example, if we had some polymeric system, we get breaking of the backbone bonds, we get breaking of some of these branches off of it. And so this decomposition process is often called pyrolysis. So in this decomposition process, we start to form lower molecular weight species, and these lower molecular weight species, through pressure and also from diffusional processes, begin to come out of the matrix. And so there's some types of materials that melt, and so there's a melt and volatilization process. For other materials, there's just this thermal degradation process where, again, there's bonds are being broken, fracturing is occurring, and again, flammable vapors are coming out. Now, it may not be the case that the lamp or heater is what actually causes the ignition process. We might imagine, again, that just like we did with the liquid ignition problems, that there's some sort of electrode or some sort of external flame that sits above the system. So this is our pilot source. The flammable vapors, so these are actually just fuel vapors. I should have talked about that. So these fuel vapors are hot because we've heated this relative to, say, the environmental temperature. Let's say the environment was at T0. And so you get a buoyant plume of these vapors, but what that buoyant plume is also doing is it's entraining air from the outside of the region that's being locally heated, and that is in fact what causes us to have this flammable mixture. So as we discussed with liquid problems, the mole fraction at the igniter still has to sit in a flammable range, and it's of course more complex with the decomposition products from a solid. It's not simple and clean. It's not typically one type of flammable vapor. It's a mixture of flammable vapors. And some of those rules that we talked about in terms of what is the lower flammability limit of a mixture would apply to the analysis here. But once we have that flammable vapor mixture and this pilot source, then we clearly will get a flame at the surface, and under conditions where the airflow rate is not too large that it blows it away, or that somehow the radiant panel is still needed for heating. So given suitable conditions, we get some established burning on this surface. So we get some flame on this surface associated with that. And if the surface were larger and we had somehow had a localized heating process, we imagine that we'd get some sort of flame spread process along the surface of this material. So what we'll first talk about is the condition or the analysis that we would use to get this ignition process. In the next lecture, we'll talk about what's required to get a spread of this flame over the surface. So first of all, let's talk about heat fluxes in sort of practical scenarios. We understand that the solar irradiance, so an average solar flux on the Earth is about 1 kilowatt per meter squared. For the ignition of cellulosic materials, it's really a range, but probably the minimum ignition heat fluxes are 10 to 20 kilowatt per meter squared. And for a fully involved room fire, we're talking about somehow between 75 and 150 kilowatt per meter squared. Now, these are high heat fluxes, but you have to think about other types of heat fluxes that you might look at in practice. So within an engine, for example, so in cylinder in a spark-ignited engine, the types of heat fluxes that you might be able to get when the flame propagates towards the wall. So this is an SI engine. Would be on the order of, say, 2.5 megawatt per meter squared. If you had an ablation problem, so say a reentry vehicle, so a capsule entering the atmosphere, and you have this bow shock and you have this localized heating of the thermal protective system. So this is an SI engine, and this is associated with flame wall interaction. In this reentry problem, depending on the speed of the capsule, we can easily see 10 megawatt per meter squared. And again, this is a gas to surface heat flux. In a rocket nozzle, where you're trying to protect the airframe, and you have these hot exhaust gases and through the throat, you could easily see 30 to 50 megawatt per meter squared. So there are lots of very high heat flux conditions. Fire is, in some sense, a moderate heat flux process compared to some of these more challenging heat flux environments. So let's just, where does solid ignition play a role in terms of the overall evolution of the fire scenario? Well, when we saw that video with the Christmas tree fire, and we have hot products on the order of 700 C, and if you think about a heat flux on the order of 10 kilowatt per meter squared, so this is our 10 kilowatt per meter squared, 10 to the 4 watts per meter squared. If we model this as a black body source, so the smoke in the upper layer of the fire, and how could we do that? Why should we do that? Well, the mean absorption coefficient for the soot is much larger than mean absorption coefficients for the gases, whether it's H2O, CO2, or CO, and the system actually becomes optically thick on length scales on the order of 1 meter. So if you're thinking about a 2.8 or 3 meter high room, then once you get 1 meter of filling, you're optically thick in terms of the radiation. And so your effective emissivity for that layer looks like 1. I mean, your transmissivity looks like 0. And so it's easy to model it in some sense as a surface radiation problem. And so looking at it as a surface radiation problem where we apply the Sefton-Boltzmann type relationship, we see that with an emissivity of 1, the Boltzmann constant here, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th, and some characteristic temperature. The temperature that we would get is about 700 C. So once we reach such these types of temperatures, this is really what we think about in fire as being representative of what's called a flashover condition. So I think we've discussed this before, but flashover refers to the process where we have full involvement of the room because the heat fluxes are able to ignite fuel packages away from the fire. So the direct fire heat flux is relatively small, so this Q direct is much smaller than this Q upper layer. And when the upper layer reaches both a thickness, an optical thickness that's sufficient, and also a temperature about 600 C, 700 C, flashover occurs. And again, this is full room involvement. And it's associated with really the heat fluxes to fuel packages in this lower layer. Okay, so we're painting the picture as to why the heat fluxes are important, where the heat fluxes come from, but we want to understand better how we would be able to model this. So we talked a little bit about the fact that, again, there's an external flux that may come from a radiant panel or it could come from this hot upper layer that's radiating onto the surface. Typically, there's some reflective loss, but that's less important really. There is this pyrolysis process that we talked about within the solid, within the condensed phase. So this is the material degradation kinetic process. That releases the volatiles and pyrolysis products that get out and eventually combust. And if we think about this more or less as a series of related and required steps where the ignition process is required, the ignition time can be thought of as depending on a time for the heat transfer, a time for decomposition, a time for the mass transfer process, a time for the mixing process, and a time for the ignition in the gas phase. Then when we look at in this form, so let me make sure I define these things for you. So THT is the characteristic time for heat transfer. Tau decomp is the characteristic time for material degradation. Tau MT is the time it takes the volatiles to come out. Mixing time. This is the air and the volatiles mixing. And tau ignition chem is the time it takes for the gas phase ignition or the gas phase reaction. Okay, so the ignition time on the gas phase, once we have a pilot, is very short. So this is really a microsecond type time scale. So let's put it as 10 to the minus 6. So this is on the order of 10 to the minus 6 seconds. The mixing time, this is a fluid mechanics time scale. So we talked about the fact that buoyant processes have velocities that look like 5 centimeters per second. So our time scale for mixing looks like a length scale divided by the convective velocity, characteristic convective velocity. So let me just put that here. So it looks like some characteristic length scale divided by some characteristic velocity. So if we're talking about maybe a sample on centimeter length scales, so 10 to the minus 2, and our convective velocities are uncomparable, so this is 10 to the minus 2 meters. U characteristic, we said centimeter per second, so similar. So all of a sudden, tau mix looks like, say, 1 second type scale. Tau decomposition at the types of temperatures that we're interested in will look like on the order of a few seconds. So we're going to just put a second here. And this is, again, like a chemical time scale, but it's a chemical decomposition time scale. The mass transfer time scale is slightly faster than the heat transfer time scale, only because the heat transfer time scale is purely diffusional, whereas the mass transfer time scale has a convective component to it. So the pressurization inside is the thing that drives out these gases. And so when you're doing any kind of serious heating in this system, this is less than 1 second in terms of overall time scale. So now the question becomes, well, what is the time scale for this heating? Well, really what we're going to do is we're going to spend our time thinking about what the time scale is for heating. But you'll see pretty quickly that the time scale for heating could be on the order of tens of seconds to hundreds of seconds. So we're going to look at a range of heating time scales, and we'll see that really this is the thing that's rate limiting. So the heat transfer process is rate limiting. And a good approximation for the ignition time is the time associated with heating up the sample to some empirical ignition temperature. Okay, so scaling again tells us approximately how long some of these other factors are and tells us that it is heat transfer itself that controls it. Now, fortunately, this is a really easy heat transfer problem because all it is conduction. We're only looking at the heat transfer within the sample. We're not interested, or we can couple it to the external, whether it's radiation, convection, or a combination of radiation and convection. And typically the way we think about it in fire is we categorize this ignition process as being either thermally thin or thermally thick. Now, if you recall, one of the parameters that we've discussed in this class is this BO number. So if you, again, recall our discussions about this, we said the BO number is the ratio of the conductive resistance divided by the convective resistance. So that's one way we talked about it. We also talked about it as the temperature difference within the sample relative to the temperature difference between the sample surface and the fluid adjacent to it. Just to provide that diagram that we had before, we said that, say this is the temperature on the inner surface of the sample or the backside. There's a fluid over here at some T infinity. We said that there's a range of values of T sample surface that we might imagine to take place, and that relative to, in some sense, this ground state of T infinity, the BO number tells us which one of these we're sitting on. So at small BO numbers, delta T in the sample is small relative to delta T across, whereas at large BO numbers, the sample temperature at the surface is essentially the same as T infinity. So again, this is the BO number increasing. Okay, so as we said, there are two limiting cases, thermally thin and thermally thick, and realistically they also, in some sense, are associated with a thin sample. So if I had a sheet of paper that I'm interested in the ignition process for, and I have a radiant panel, I'm going to assume that the temperature distribution or the temperature gradients are small inside this sample compared to any representative temperature difference between my source or even my convective sink compared to the sample. On the other hand, if I'm interested in the ignition process for a compressed, and so imagine this is a compressed solid material, then the thick assumption says that the diffusional transfer through this is going to be so slow that by the time I hit an ignition temperature on the surface, I still haven't seen the backside of this thermally. So in heat transfer, we oftentimes call this a semi-infinite approximation. So here we see the thin case where it's essentially isothermal. The front temperature is essentially the same as the back temperature. Whereas in the thick case, we may imagine that the back temperature is over here somewhere, and it's always held, it's not always held, but remains at this initial temperature. And at the time of ignition, the thermal wave has not yet reached the backside. So the extent of this thick sample does not play a role in the ignition characteristics. So this thermally thick, in heat transfer literature, I'm having problems spelling infinite. Infinite. Wow. Okay, so this is the semi-infinite approximation. And again, it's that the back boundary condition does not affect the thermal analysis. Okay. All right, so let's first do the simpler case, which is thin samples. So if I have a thin sample, and for this first case, we're just going to assume that this is an insulated back. We can generalize it as necessary. So the question is, how long will it take a thin sample to reach its ignition temperature? The assumption is that we have this sample of thickness, I believe that we're going to use D here, of thickness D over some insulated backing material where an external heat flux is provided. So again, there's a radiant panel or some other heat source here. But as this thing is heating up, it can also convectively be cooled by the external flow. And this external flow could be forced, or it could just be the natural convection associated with having this hot sample in a cool environment. So it's external convective cooling. Okay, because it's thin, our energy balance is relatively simple. So the absence of gradients in this system, so the approximation that there are no gradients, allows us to set up an overall energy balance on this system. And that overall energy balance, so we take a control volume that encompasses this sample, and we say that the change in energy with respect to time for the sample, so this is sometimes called our storage term, is simply equal to the rate of energy input minus the rate of energy leaving that system. And so it's just a control mass system, as we again say, for example, in thermodynamics. Okay, so thermodynamically, because it's a control mass system, we say that this energy, in fact, what we say is that change in energy is equal to specific heat capacity is equal to, so capital I'm going to say it's extensive, is equal to the mass of the sample, the specific heat capacity of the sample, times the change in temperature. Okay, so in many respects, really, what we've said is that we've used the property, we've used the definition of specific heat capacity here at constant volume and said that that is just the change in internal energy with respect to temperature. Because this is extensive, we have the mass of the sample there. So our rho, I'm going to make this so because I'm not confused with velocity later on. So our rho v is our mass, CV is Cp for these condensed phase systems, so we're not differentiating between that. So here is that MCV term. So again, M is rho times the volume. So rho times specific heat capacity. Make sure we're all on the same page here, that this is the specific heat capacity at constant volume. And of course, rho v is our mass. So rho CV dt dt is equal to our energy input. A here, A here is it's our surface area, and it's our surface area. Let's just say surface area, minus our Newton's law of cooling, E out description, where again H is our heat transfer coefficient. Okay, so we're just expanding this, and we're perhaps using one form of the radiative transfer process as epsilon sigma t to the fourth minus t surface t infinity to the fourth. So this is just an expansion of the radiation term. Now, oftentimes we can linearize the radiation term, again, just as a convenience. So if we have our epsilon sigma, say t to the fourth minus t surroundings, or t infinity to the fourth, we simply can factor that as epsilon sigma t squared minus t infinity squared t squared plus t infinity squared. Further factoring, we have epsilon sigma. I'm going to put it as t squared plus t infinity squared. Now I'm going to factor this as t plus t infinity, and then finally t minus t infinity. So all this stuff, sometimes people think about as a radiative heat transfer coefficient. It clearly depends on the temperature. So it's a nonlinear dependence. And so as this, just as a construct, we understand that there is a linearization that's possible under conditions in which we've linearized. We might think about having an effective heat transfer coefficient, where that effective heat transfer coefficient, in this case, is nothing more than the convective plus the radiative component. And as you know, because this is a first order system, there's a characteristic time associated with this process, where we've simply defined the characteristic time. I mean, this is obvious, but if we looked at this as dt dt, we see that dt dt is equal to minus h effective A over rho CV times our delta T, right? Well, given the fact that this is units of, say, Kelvin per second, clearly this has to have units of Kelvin per second right-hand side. So again, we can infer that rho CV over HA has units of time, and that is in fact our characteristic time. We understand that the solution of this is a simple exponential. So we integrate this thing once. We get T minus T infinity over T0 minus T infinity, where T0 is the initial temperature. And since what we're interested in is the time it takes to get to a particular temperature, which we might call an ignition temperature, we take the log of this, both sides, and we get a relationship for time in terms of our characteristic time. And when we specifically call the time the ignition time, so what we're asking is, we ask at what time will the sample reach an ignition temperature, and we answer it by saying it's this specification. So it's tau minus tau log T ignition minus T infinity minus, take it to minus 1, and so it's tau, so just invert it, okay? Okay, so sometimes we call this in the language of many fire books the long time thin ignition analysis. And so I need to be careful here. The long time here refers to the fact that in this approximation, the convective losses become important. And there are problems where the convective losses aren't important, and those are going to be short time. In fact, I'm going to talk about that right now. So let's break out of this for a second. So let's do an insert. Okay. So let's ask, what does it mean to be at long time versus short time? And I'm going to do this problem just a little bit differently from what we just did. So again, we have this thin sample, and I'm just going to put this as Q external. Again, referencing this as HT infinity. Okay? Just as we had set up before, now I'm not going to linearize it. Of this Q external. And so just as we had rho CV dt dt is equal to Q E A minus H A T minus T infinity. Okay? So this is just like what we had, except we're not going to hold on to that. Okay, so here's what we're going to do. You know, there are some really interesting aspects to this problem. So let's just, for fun, we understand that this problem has a steady state solution. So let's just say that there is a steady state. And the steady solution is the one where dt dt is equal to 0. And obviously what that says is it says that the steady state temperature is the temperature associated with this system, or that T steady state is equal to T infinity plus Q external over H. Okay? So in steady state, what else does it say? It says that in steady state, this sample heats up to a temperature where the external heating is exactly equal to the convective losses. Makes sense, okay? So there's no longer storage because it's in steady state. Okay, so based upon that, we can pose this problem as one in which we can now say, okay, well, this is rho CV, let's just play it out simply, is equal to minus H, let's do this right. So what I'm going to do is I'm going to substitute T steady state into this problem. So T steady state is, again, T infinity minus Q double prime over E. Okay, good. So we see it's minus H A T minus T SS. Okay. So let's just, again, let's verify that. It's H, T minus T infinity is pretty clear. Minus H A times QE over H is going to give us QE times A with a positive sign, which is what we have there. Okay. All right, now, so let's call theta t minus t steady state. And so we have d theta dt is equal to, and we're going to use our characteristic time definition again, minus theta over tau, where tau is our characteristic time. So the solution for this is theta over theta 0 is equal to exponential minus t over tau. So no big surprises there. It's very similar to what we had before, just with the interpretation that this is t minus t steady state divided by t0 minus t steady state, okay? And so again, this is our long solution, okay? So the long solution has this log dependence like we had before. But imagine a scenario where we never get anywhere close to t steady state. So what if ignition happens or ignition takes place in quotes long before t looks like t steady state? And so let's think about it mathematically first. So mathematically, and then we'll talk about it more intuitively. So really what we're saying is that what if t ignition minus t steady state over t0 minus t steady state is basically 1. Okay? All right, so what am I saying there? Well, what I'm saying is that what if the difference between t steady state and the ignition temperature is almost as big as the difference between t steady state and the initial temperature? That is, that the ignition temperature is closer in value to T0 than to T steady state. Okay, that's what that means. All right, I need another sheet here. We're going to keep that so you'll have it for your notes. Okay, so what we said again is that T ignition minus T steady state over T0 minus T steady state, and sort of looks like 1, but maybe there's a correction. But we know that what it really equals is it equals exponential of minus t over tau. That's what we know it really equals, okay? So we might ask ourselves, what is that correction? Well, let's play a game here. We know this correction is probably small, so this thing is small. So the game that we play is, if we think about exponential of any function, the exponential function, so exponential of x, if you did a Taylor series expansion for this, you'd get 1 plus x squared over 2 plus, and it just, so we go on. So the first term in this is 1 minus t over tau plus some higher order terms. If truly this looks like 1 plus small terms, then maybe the first order term is just the most important factor. So based upon this, we get that that T ignition minus T steady state over T0 minus T steady state is equal to 1 minus T over tau, or T over tau is equal to 1 minus T ignition minus T steady state over, I'm just going to, yeah, T0 minus T steady state. All right, we're almost there. So this is T0 minus T steady state minus T ignition plus T steady state over T0 minus T steady state. Okay? So all I did was put that in there. And so we lose this guy. And so I'm going to just do one more thing, which is then T ignition minus T0 over T steady state. Well, all right, so T steady state minus T0. Okay, so I just switched the sign on the top and the bottom. I'm going to put this over here, which says, again, now T over tau is equal to T ignition minus T0. You're going to laugh when you see the final result here, or maybe not laugh. Okay, T steady state, we said, is equal to T0 plus the external flux divided by the heat transfer coefficient. Now, this is minus T0, so this is TSS. So this guy cancels out, and we get that this is equal to T ignition minus T0 over the external flux divided by H. Now, what the book and text will say is, they'll say, okay, well, T ignition is equal to our characteristic time, rho CV over HA, times this T ignition minus T0 over Q divided by H. Okay? You get the message, but we do actually need one more screen, one more. And what that is, the message is, that T ignition is equal to, I think I had rho CV. Okay, so rho CV, I'm going to write V as A times D divided by HA times T ignition minus T0 over Q over H. So we get rho CD T ignition minus T0 over Q triple prime, over Q double prime external. Okay, so that's what we get. So there was a lot of math in that. There was not a lot, but there was some math to get that. There was some analysis required. Could we have done this simpler? Yes. So with more physical intuition, we can go back to our original differential equation, rho CV dt dt, where, again, the physics is storage / transient. This external flux and this convective loss, and use what we started off with. We said, from an intuition perspective, short ignition times might refer to a scenario in which we said this, all right, so I'm not making this up, that T looks more like T0, which looks like T infinity. The T ignition, let me say that, T ignition is small compared to T steady state. So what we did in that analysis really is we neglected the convective losses. So all that analysis boils down to, for these short times, to neglecting the convective losses. In which case, dt is equal to Q. We're going to divide by rho CV. And it's just rho CD because, again, V is A times D. And when we integrate this, it's trivial. It's T ignition minus T0 over T ignition is equal to Q over rho CD, or just the result that we had before, T ignition is equal to rho CD T ignition minus T0 over the external flux. Okay, so you'll need to apply this to some simple problems. T ignition will be given for a range of materials. And we'll go through the process of saying, well, what time will it take for this to ignite, given a specified T ignition, specified heat flux, a particular thickness, density, and specific E capacity. Again, there are tabulated parameters. Okay, now for the thick case, this is a much harder mathematical. Well, it's much harder. It's a harder mathematical problem. It's a linear differential equation. Some of the approximations that we make are that the properties, and this is an important issue, that the properties are in some sense calibrated for the temperature that we believe is the ignition temperature. So you have to think about that for a second, because this is sort of a weird issue. If you think about the actual ignition of a material, even if it's a thin sample, so if I had a lamp heating up this piece of paper, it would start to blacken and char perhaps before it actually ignited, before a flame was supported above it. It's hard to imagine that the properties don't change as this decomposition process is happening prior to ignition. So in some sense, what we do is we're taking a representative set of thermal properties that corresponds with this indicator for ignition, which might be this temperature, surface temperature, and we're using that to predict in other scenarios what might occur. So you can think about this as really as calibrated parameters for the scenario of interest. And what that means is that there is some uncertainty that would occur if you simply use the virgin properties of the material, the material properties prior to any decomposition. If that's all you have, you understand, of course, that there is some error, and that should be something that should be stated. All right, and that's true whether it's a thick case or a thin case. As we said, semi-infinite approximation is that it's semi-infinite over the time of interest. That is, that over the time associated with ignition, the thermal wave has not yet reached a true backside of this sample. And I'm not going to just go over that again, because I think we've said it enough times. Oh wow, this is terrible. Okay, so this is wrong. So what I'm trying to say here is that the thermal diffusion, this thermal penetration distance, scales like the square root of alpha t. Okay, so it scales like the square root of the thermal diffusivity times the characteristic time. That comes right out of the differential equations. Let's say delta is the thermal diffusion distance, and it's a time-dependent thermal diffusion distance. And as we said, it scales like thermal diffusivity times the time of interest square root. So, give me an example. All right, if the thermal diffusion coefficient, if alpha, say looks like 20 times 10 to the minus 6, so, this is air, and we're interested in a characteristic time of 100 seconds, let's say 200 seconds, so it's easier to do the square root, then the product of alpha times tau is 4 times 10 to the minus 3, right? 10 to the minus 4 and an extra 1, 10 to the minus, yep. So it looks like the square root of 4,000. So delta for, is that right? All right, let's see, 10 to the minus 6, 200 seconds, 40 times 10 to the minus 4, 4 times 10 to the minus 3, square root. Oh, yeah, that's right. Okay, good. So it hasn't penetrated, I mean, we're talking about, what is that anyway? That's 0.004 square root. So it would be, would that be 6 times 10 to the minus 4? Approximately, between 6 and 7 times 10 to the minus 4. So, like, what is that? So 0.6 millimeter. So 6 times 10 to the minus 4 is 36 times minus 4 times. Oh, we should just use a calculator for that. But as you can see, it doesn't. No, that's not right. That's 6 to the minus 2. Maybe closer to minus. It can't be minus 2 even. It's minus, obviously minus 1.5, whatever that is. Okay, so 6 times 10 to the minus 1.5. So it's clearly smaller than a centimeter in terms of how far it's diffused into the system. Okay, so diffusion is slow, and it takes a long time to diffuse into anything with a moderately small thermal diffusivity. When we look at again, the scaling analysis explicitly pulls out the thermal diffusivity by just dividing the thermal conductivity by rho c. And there are lots of different ways to solve this differential equation. Laplace transform methods can use it, similarity transforms, etc. Okay, we're almost done. Now, so one thing that helps us is this scaling process. If we look at a problem, this is not right, I'm sorry, constant surface heat flux. So when we look at a constant surface heat flux problem, so this is a case where we have Q external on some surface. This is the in-depth profile. One thing that we have to take into account is if this is really a constant heat flux, then the boundary condition internally is that minus k dt dx at x is equal to 0 is specified. That means that if it's a true constant surface heat flux problem, dt dx is always the same at that interface, and that's what we're showing there. Approximately, we can think about this as just straight lines, where each line is delta at some particular time. So this is perhaps delta at t1, delta at t2, etc. So from a simple scaling law, so from perhaps a definition of Q in terms of k delta t over this delta of time, where we use the scaling for this diffusion distance, we get the surface temperature increases like the square root of time. Okay, and obviously the thing that we're searching for here. So I'm going to put it here. I'm going to insert a new slide. Okay. So the thing we're looking for, so we said that T, S of T, in fact, I'm going to write it, I'm going to start from here. So we said Q external, or Q surface, I think we called it over there, is equal to K TS minus T0 over the characteristic distance. This is alpha T. And we're going to break this out a bit. So alpha, of course, is K over rho C. And what we're going to do is we're going to square all this, because what we're interested in is we're interested in the ignition time. And so when we square this, both sides, we get, again, QS squared, K squared, TS minus T0 squared, divided by K over rho CT. So we get K rho C, TS minus T0 squared over T. And when we associate T with the ignition time and we solve for it, we get T ignition is equal to this K rho C factor. Now we're going to call TS T ignition minus T0 squared over this QS squared. Okay. Now, this is great. It's correct, but it's only correct really in this short ignition time model. And it's also it's correct in the short time limit approximation, and it's also correct only from the scaling analysis perspective. Okay, so in this, we didn't actually solve this with the similarity transform and all the other good stuff that we should have probably solved it for. And so the true physics of the problem, let me see if I find this here. The true physics of the problem would have just a slightly different dependence. And so it's different by, so in the actual, without scaling, with using the full solution, we would have had a pi over 4 here. So the pi over 4 factor, which, you know, 0.8, 0.75 something. So that is the correction associated with actually solving the differential equation. Last thing I'm going to say is that in the long time limit, the ignition time looks like K rho C this is sort of interesting. T ignition minus T infinity squared. Okay, so remember, long time limit, this means that convective losses are important. And I want to give you some insight into what this really means. You know, so how is this related? That's, I mean, there should be in your mind, you say, well, gee, is this similar in any way to the short problem? And yes, it is. So in the long time limit, you have this Q external. I'm going to put V here. You have this Q external,
And now we're saying that, I'm going to say that there's a Q internal, and there is a convective. Where's a Q convective? QC, Q convective. So this says that if it's a long time, then the stuff that's useful inside is Q external minus Q convective, and the temperature that's associated with the ignition process looks like Q external over H. So if we put this together in this long time problem, it says that the long time problem can be thought of almost the same way as the short time problem, where it's again just T ignition minus T infinity over Q internal squared. Okay? So remember what the in the short time is T ignition minus T0 over Q external squared, but we had the Q external was the amount of heat that was heating up the inside also, and here it just looks like it looks exactly the same, but we're taking away some of Q external that's associated with the heat losses. Okay, all right. So this is a good place to stop, and next lecture we will talk about how this impacts flame spread processes.